Hello, this video is on light interference and diffraction. A reminder, hopefully from a previous physics class, although I know with the crazy couple years we've had, this might not have been covered in your class thoroughly, but all waves use what's called the superposition principle of interference to determine what happens when two waves meet in a medium. The superposition, sorry, this is a not high quality image, but anyway, the superposition principle works as such. If you have a wave moving to the right, a small wave moving to the right, and a small wave moving to the left, when they meet in the middle, it makes a big wave right in the middle. And thus the height of that wave is the sum of the two individual waves. So if each of those individual waves is 1 meter tall, this is going to be a 2 meter tall wave. After they interfere in the middle, those two waves just pass right through each other. So those two waves would continue moving in opposite directions through the medium. And this is known as constructive interference when the waves are on the same side of equilibrium because it makes a bigger wave, right? A +1 and a +1 makes a +2 wave. You'd also have constructive interference if those two waves were on the bottom of the medium and they merged to make a -2 tall wave. That would still be constructive because that's a bigger amplitude wave. There's another kind of interference known as destructive interference. So if the waves are on opposite sides of the equilibrium as they're moving towards each other, so if I have like a +1 wave and a -1 wave, when they meet in the middle, the medium actually is flat for a short instant in time, and then the two waves are going to pass through each other, so moving on through the medium in opposite directions. So that's, in general, a quick refresher of what is the superposition principle generically for all waves. So how does superposition work with light waves? Well, light waves tend to be continuous waves, or we think of them as, a wave packet, not just a single pulse of light. And when we talk about interference, we are usually talking about interference of light with another light wave that has like the same wavelength with it. And so how do we get constructive interference with light? Well, if we have two light waves, and those two light waves are perfectly lined up with each other so that the crests are at the same location and the troughs are at the same location. Well, you can imagine if you were talking about superposition, adding these two waves together, what you end up with is a wave that is twice as tall, right? That wave, the resulting wave is going to be twice as tall because it's going to be the sum of those two individual waves. So if two light photons arrive at my eye at the same time, and they are what's known as in phase, that means the crests and the troughs are coming together, my eye and my brain are going to infer that we're looking at a really, really bright light. Now I could take the same two light waves, but if one of those light waves is out of phase, that means one of them is cresting while the other one is troughing. Well, we have exactly the opposite scenario. Those two light waves are going to destructively interfere, and we end up having a resulting light wave that has a much smaller or zero amplitude, and that's going to look dim or dark. So this is sometimes called out of phase, as I mentioned, or sometimes they mention a phase shift. So if you think of a cycle, 100 or 360 degrees is going to be one full cycle. So if you're shifted by 180, that means the top matches up with the bottom of the other wave, and that's going to be a dim or dark piece of light. It's going to appear dim and dark to your eye. An interference pattern is like a photograph that documents interference between different light waves, and it shows the dark and light spots created by different photons arriving either in phase or out of phase with each other. And we'll talk about how do you make interference patterns in a minute, but I wanted to just introduce the name and the idea that the bright spots in this picture are places where light is constructively interfering, and the dark spots are places where light is destructively interfering. This is interference pattern also, one that you have actually probably seen in your life, of an oil on a little piece of water, and a little preview, we'll be coming back to that in a future video, but just so you know that that is a function of light superposition as well. So the primary mode of creating these interference patterns that is on the AP test is known as diffraction, usually two-slit diffraction. So the way two-slit diffraction works is you have a screen of some kind that has two little gaps in it. So that's right here. We've got some kind of like solid piece of material, and I've cut two tiny gaps in it. And I shine a light on the on this screen from one side. So this right here is representing the light that is coming, my incident light. And those bars are representing like the crests of the light. We're kind of like a top-down view of the light, so the wave is going in and out of the screen, and those bars are representing the crests. So what happens when that wave hits these two slits is the wave goes through the slits, but it spreads out. And you can picture this just like a water wave, right? Imagine a water wave would do this going through two slits. It doesn't just go straight through the slits. We don't make these little, like, doesn't just keep going straight like that. You actually end up with this spreading out of the water wave, or of the light wave. And when it does that, the two slits kind of become new wave sources, right? You know, it's kind of like, you know, two speakers or something that are creating waves that are spreading out around them. So we have like these two new little wave sources that are created at the slits. And because they spread out in two dimensions through those slits, there are places where the crests of those waves are going to match up and line up with the crest of the other little wave that's coming through. And those spots, those locations, end up being locations of constructive interference because we have two crests at the same time. Now, in that 3D space, there's other places where you have a crest matching up with a trough. And I'm writing that in yellow here. You can kind of see, right? Right on that line, everywhere on the line, we have one crest matching up with another, with the trough of the other wave. And so those locations are going to be destructive interference or dark. If you project this on a screen, so if you make a screen that kind of cuts this pattern at a certain distance away, the pattern that is created on the screen looks like this picture right here. Okay, where we have the bright spots, right, at certain locations on that screen, wherever the crests are lining up. Bam. Okay, so every time that that the two waves come back together in a constructive way, we get bright on the screen. And every time the two waves are destructively interfering with each other, we get this dark spot on the screen where the wave doesn't really appear to be very bright. Another way of showing this, just kind of like with the way, you know, sometimes it's hard to do the top-down view, so this is like, you know, a little bit of a different view of it. The location right in the middle, right, which is exactly the same distance from each of those two little wave sources, is going to be a bright spot because the two waves have gone exactly the same distance to get there. And that spot is known as the central maximum. These spots get numbered, as you can see, with m equals 0, m being the number of bright spots away from the central maximum. So m is 0 is the central maximum. And since the two waves from the two slits have traveled exactly the same distance, and they were in phase when they left, right? Because this is a single wave, so they're in phase when they hit those two slits, and they've gone exactly the same distance. We are going to always have constructive interference at that spot right in the middle of the two slits. Now, if you move a little bit further away, okay, what happens is one of those waves travels a shorter distance than the other wave does to get there. So even though they started in phase, this wave, wave number 1, only had to go this far to get to that spot, whereas wave number 2 has to go a longer distance. And so what that does is it takes those two waves out of phase with each other, right? Because if that second wave had to travel exactly a half of a wavelength more than the first wave, then it's going to be out of phase by 180 degrees, and we get one of those dim spots where we effectively have a phase shift caused by the difference in the distance that the two waves had to travel to get there. Then, of course, as we move further away from the central maximum, there's a bigger and bigger path difference, but eventually we're going to hit a spot where, you know, wave number 1, I should have drawn these in yellow, but wave number 1 has traveled, you know, this distance, and wave number 2 has traveled exactly one wavelength further, and so we are brought back into phase, and we get constructive interference again. This is a phase shift. It's a 360-degree phase shift. And so we are back in phase with the original wave, and we get constructive interference. We would say that's so the path length, this L, is one full wavelength difference. Incidentally, there is this really useless equation on the equation sheet, but just so I've covered all the equations on the equation sheet, it basically says what we were just saying. If the difference in path length is some integer number of wavelengths, we get constructive interference. So this m equals 1 is getting constructive interference because it's, the difference in the lengths, that the distance those two waves traveled is exactly one wavelength. You get constructive interference at exactly 2 wavelengths and 3 wavelengths and so on for all of the different bright spots. Another synonym, by the way, sometimes those are called fringes, not spots. So just so you are aware of that terminology. Okay, a very common AP2 problem is an experimental style problem using diffraction. Unfortunately, we're not in the lab. There will be a PhET simulation that you can do that can simulate this, but try to follow along as we go through what an experiment about two-slit diffraction might look like. So the setup is as follows. We would start with a source of monochromatic light. Monochromatic means all the same color, and that is usually provided by a laser, right? So we've got this laser coming in, and the light is all the same color, and it's also all in phase, which is kind of a cool thing about lasers. And we would know the wavelength of that light. Usually when you buy a laser, you can read that right off the laser. So that light is incident on, or it hits a screen that has two slits, just like we described in that last slide. The spacing between those slits is known as variable d for the distance in between them. So that light is going to pass through the slits, and we're going to start interfering on the other side of those slits like we showed in the last slide. And we are going to then be placing a screen, some kind of projector screen, a certain distance away, and that distance will be described as x. So x is the distance to the projector screen. And the interference pattern is then created on the screen, and the variable y describes the distance between the central maximum and the first spot. Incidentally, y is constant here, so the distance between the first and second spot is also y. Distance between second and third is also y. There is a spot here for various reasons of math. That spot ends up looking really dim, so you actually can't see it in the image, but it is there. And then we have another y, etc. So if you were asked to find, the distance to the fourth spot, all you got to do is find the y spacing and then multiply it by 4 to get the distance to that spot. Okay, so the question is, this is a common question on both multiple choice and FRQ. How would changing these variables that we can control in this experiment impact this y value, impact the spacing of those spots on the screen? Okay, so let's tackle them one at a time. Y is going to have a linear relationship with lambda. The bigger the wavelength that wave has, the longer the L has to be, according to that equation that we actually got in the last slide, in order to create constructive interference, right? We have to move further on the screen to have a path length difference that lines back up again constructively. So we have a linear relationship between y and lambda. So in an equation, if you double the lambda, you're going to be doubling the distance away that the first bright spot is from y. And that's of course going to be relevant because doubling lambda is like changing the color of the laser. So different lasers are going to have different wavelengths, are going to have different diffraction patterns created on the screen. And in general, right, higher wavelength colors like purple, purple has a smaller wavelength, and so that's going to have a smaller y as well. Y also has a linear relationship with x, and this should make sense from just like a geometry perspective, right? We have this triangle created. If I drew my screen somewhere closer here, well, obviously that distance is going to be a smaller distance just based on the way projections kind of work. So it's all geometry of like triangles. The further away you place your screen, the bigger the y spacing is going to be. And the last relationship is y actually has an inverse relationship with the distance. which means that the closer the slits are to each other, the further apart the spacing of the pattern is on the screen. And that's a little bit counterintuitive until you kind of think about it in terms of that last slide where I drew the waves, right? If those slits were really close to each other, that means that the length of the path is going to be very similar as you start moving up and down, right? Because there's not much of an angle difference, basically. And so you have to move a lot further before one of those waves has traveled a whole wavelength more than the other one. So there's an inverse relationship due to geometry between the distance between the slits and the spacing of the slots. So I would write this equation like this if I was in charge of the world. Y has a linear relationship with lambda and x and an inverse relationship with d. The m in there is reflecting the number of spots away, and that's just, the m is basically the multiplier that I mentioned earlier. If you're 4 spots away, it's just 4 times the distance. However, on the equation sheet, they give you something different, which is this: d sine theta equals mx, or m times lambda. The same relationships are represented in that equation, but I've never actually seen that equation used. And there's the equation they gave actually only works when theta is a very small angle. So in their equation, this theta is going to be this angle right here, in between the angle between the two dots, the central maximum and the first dot. And this to me is a pretty useless equation, because imagine trying to measure that angle. Like, imagine in a lab actually trying to measure that. Like, it's pretty much impossible, whereas these things are all things that are measurable and useful. So this might be the only equation on the exam that I think that you should memorize and know that is not on the equation sheet. I think this is a useful one to have, and it is just a better way of saying this equation, which is on the exam. But even if you don't memorize the equation, knowing these 3 relationships is going to be pretty critical to getting points for sure on multiple choice, and maybe on a big experimental problem as well. Occasionally they throw a weird problem at you that has more or less slits than 2. And I'm not going to go through all of the math that shows you what patterns we actually get. But I want you to know that you get the same pattern with any number of slits. Okay, so whether you have 1, 2, 3, 4, 5, 6, or 7, or infinite numbers of slits, you get the same patterns. But the more slits you have, the more defined the bright spots become, and the more defined the dark spots become. So this 7-slit pattern, you can see, really looks like dots. And again, there actually is a dot there. You can actually see it in the 2-slit number. It's just really dim based on math. Any case, you have the same pattern no matter the number of slits, but we have more defined bright spots the more slits you have. So that's just something you should kind of be aware of, because sometimes they give you a qualitative question that says, if we change the number of slits, what would change about the pattern? And the answer is the more defined they are. This is a kind of a different way of looking at it, a graph that shows brightness versus location. And you can see for the as you increase the number of slits, we get more, the spike is taller and the gap is shorter, or is lower in between them. So this is like brighter dots. Single slit diffraction is similar as well. Things kind of blur together via mathematics. I don't think that'll come up on the test, but anyway. The last thing you should be aware of is something known as a diffraction grating. That just means basically so many slits, right? So diffraction grating is like just all the slits. It's just a very fine-toothed number of slits, and that makes something that has very well-defined dots. So just for fun, let's do a couple thought experiments here. I kind of referenced this earlier, but how would a green or a purple laser create a diffraction pattern through a diffraction grating that would look different than a red? So pause for a second and think about it. Okay, so here's a picture of the same diffraction grating with all 3 lasers through it. And you will see the main difference is that spacing, that y distance from the central maximum, decreases as the frequency increases. So it's inverse with frequency, or it's linear with wavelength. So as the wavelength goes down, the Y value goes down as well. So different colors of light create patterns that have different spacings. Second thought experiment, what would happen if you put, now we're back to just the plain red laser, but I have two diffraction gratings that are at right angles to each other. So I essentially have this, and then on top of it, I'm going to make another diffraction grating that looks like that. What are we going to get? So take a pause and think about it for a minute. All right, I think most people jump to the like polarizing filter situation and think that that's going to maybe destroy the light completely, but that's not what happens for diffraction gratings. What happens is as that light goes through the first diffraction grating, it spreads out into this pattern in this direction, and then when we rotate the diffraction grating, what it does is it diffracts that light in the other dimension as well. So you actually end up with a grid of lights where you've got an extra strong central maximum there, and then you've diffracted this way, and then you've diffracted this way as well. So a single laser can make a pattern that looks like that. And perhaps you've seen that kind of pattern before. Like, for example, people on the holidays have these things outside their houses where they project little pictures via laser, and the pictures are always in this square grid because they're sending them through, it's a single laser shape, and they're sending it through diffraction gratings that are overlapped each other at right angles. Last fun thought experiment, so combine these two ideas. What would happen if you put white light, like the sun, through two diffraction gratings at right angles with each other? Pause and think about it for a second. And the answer is you get rainbows. You get a whole grid of rainbows. In your physics kit, one thing we never got around to using is your rainbow glasses, and that is what your rainbow glasses are. They are two diffraction gratings at right angles to each other. And when you look at a white light source like the sun, you will see basically rainbows radiating out from all of these little points. One fun thing to do is to look at different light sources. So look at a natural light source like the sun. Look at light bulbs in your room, which are, if they're incandescent, they're pretty similar to the sun. If they are fluorescent, you'll see that they don't actually have all the colors in the rainbow in there. All they have is red, green, and blue, because those are the only three colors your eye needs to think that it's actually looking at white light. So that's kind of fun. Looking at the light on your phone is kind of a fun thing to do as well. So pull out those rainbow glasses, and now hopefully you will understand why you're seeing what you're seeing. That's all for this video. Thanks for watching.